Take a methane molecule made up of a carbon atom surrounded by 4 hydrogen atoms. According to classical physics, this molecule evolves along some definite trajectory, which might, for example, be rotation about some axis. If our knowledge of the molecule's history isn't perfect, we may need to consider several possibilities for its motion. It may happen, for example, that we know about which axis the molecule is rotating, but don't know if it's rotating clockwise or counterclockwise. In the quantum world, each of the different possible motions is assigned a special property known as its quantum mechanical phase, which varies between 0 and 360 degrees. Here we represent this phase using color, with, for example, red indicating a phase of 0 degrees and blue indicating 180 degrees. When we know for certain the quantum mechanical phases of each possibility, we say the molecule is in a coherent state, while when its phases are randomly fluctuating and unpredictable, we say the molecule is in an incoherent or classical state. Quantum mechanical phases have real, observable consequences. We can have, for example, that a molecule in a coherent state of equal phases strongly absorbs light of one color and transmits another, while if the phases are opposite, then this behavior is flipped. If the molecule is in an incoherent state, then both colors are absorbed equally. Coherence is notoriously fragile. Even when a molecule bounces off of a surface, take for example the surface of nickel atoms, the interaction between the molecule and the atoms of the surface typically destroys the coherence of the molecule's initial state, leading to a loss of the molecule's ability to preferentially absorb light of a particular color. However, in our lab we recently discovered that when a molecule scatters from a surface composed of gold atoms, the molecule retains its ability to completely transmit some colors and strongly absorb others, indicating that the coherence of its quantum mechanical state is unharmed by the collision with the gold surface. This discovery sheds light not only on the nature of the fundamental interactions governing the chemistry of our everyday life, but also on where lies the boundary separating the classical and quantum worlds.